Thank you very much for the organizer with these venues that we could have opportunity to see everybody in the same area of lithium-sulfur batteries and report some of our data on the mechanism study. So what I'm going to report today is investigation of the sulfur redox reactions by quantitatively and qualitatively measuring the dissolved polysulfide. Now, I don't think you're always starting from these slides and what is chemistry beyond lithium ion, but I think that this has been, well described, so save the time and just go beyond that. And the barrier of the lithium sulfur chemistry, and I'm pretty sure that the Dr. Offer has been explained that in very details, and I don't have anything new here, so I'm going to skip that one too. Now, when we started to study the lithium sulfur chemistry, I'm an electrochemist. So the first things coming into my mind is the fact that you only have two-step discharge and pretty much one-step charge. Sometimes you see this small bump, but sometimes you don't. Now, as an electrochemist, you're always thinking that you have multiple polysulfide species, then you should have multiple discharge plateau, or you do cyclovoltammetry, you should have multiple peaks. Why only have two peaks? So in order to understand that, and we all know that polysulfide is highly soluble, and so we're trying to study the mechanism. And so the first thing we did is pretty much like Dr. Offer said, we went into the literature and we see a lot of this mechanism, and with the polysulfide species at different depths of discharge. Now, the problem is how those dissolved polysulfide was determined. And here I just list three examples and many examples and technique. And the most common one is use UV visible, and then the Raman spectroscopies and X-ray absorption, as the previous speaker presented, have been using to identify the polysulfide species. Now, the big problem for this kind of technique is that it is impossible to make a standard pure polysulfide solution. Okay, it's possible we can make a solid phase polysulfide, but as soon as it dissolves into the electrolyte, disproportionations happened. So in that case, no matter what kind of polysulfide you made, whether it's S6 or S4, you dissolve into the solution immediately. Okay, you're going to have the whole composition of all the polysulfide species. So now, if you do not have a standard, a pure solution, it's very difficult either to use the UV visible or Raman. You can use calculations, to determine what is the peak or the energy is supposed to be, but there's no direct experimental evidence. It's almost impossible. So therefore, we're thinking about we have to give up the concept of making the pure polysulfide standard solution, and we'll have to find a technique that do not going to use. You don't need to use the pure polysulfide solution. Now we find is the mass spectroscopy. So the mass spectroscopy is not using the pure polysulfide, but rather using on the mass and charge ratio. So now for the polysulfide species, okay, even though it's in the composition of different polysulfide species, the mass and charge ratio will be determined. You know how many the sulfur attached together, and the charge on it. So in that case, you could use spectroscopy to determine that, to make things better, and we can use HPLC and to couple with the MS. So in that case, we can effectively separate each one of the polysulfide species, and using the HPLC, and then use MS to determine which one is, what is the chain length. Now, what we've done is, first of all, a sulfur analysis, you could do it using the X-ray, the absorptions and the others, because you can make a sulfur the standard sample. So and also using HPLC, UV, we don't even use the MS. we could determine the concentration of the sulfur in the solution. This is a dissolved sulfur species in the solution. And the first thing we do, we try to analyze and measure the solubility of the sulfide in the all different kind of a common solvent we use in the sulfur batteries. Then, for the polysulfide, the first thing we try, and also there's publications on the ECS, just using the LC column to separate polysulfide. But when we try to separate polysulfide, and we found that the polysulfide cannot be separated by the LC column just by itself, okay? It's just the retention time, if you're looking at this curve, the retention time of each of the polysulfide are pretty much the same. That's one problem. And the other problems, in order for us to do the in-situ experiment, we need to take a very small amount of electrolytes, microliter range. Now we have to dilute it, okay? Then run into the HPLC column because, if the people familiar with that technique, you have a flow phase. So basically it's the acetonitrile and you flow through the LPLC. Then if that is the case, the polysulfide will become disproportionated during the process because that's very fast reaction. So anything that come out of the column will not be the same distribution that you have in your cell. Now, in order to address that problem, and we find a multiple complex agent. So in that case, we complex the polysulfide species first before we run into the column. And we have done quite a bit of experiment and make sure that when the polysulfide species and complex with making it become a complex, then the further chemical reactions will be ceased. So in therefore, we're pretty much taking the amount of electrolyte from the cell and we complex the polysulfide species. We're pretty much like take a snapshot of that things. Then when we run through the column and run through the MS, you see this is the actual the data. So we can pretty much separate each one of the polysulfide species. And the peak is proportional to the concentration of it. Then you're using the MS, and you can determine, which, for example, this peak, and we can determine, what is by determining the mass and charge ratio, and we know that what is the polysulfide species coming out of this peak. So in that case, we can successfully, not quantitatively, but qualitatively determine all the polysulfide species. Now, using this one as a technique, then we can study the mechanism of the sulfur chemistry. And now this is the pretty much discharge curve. Now we did exactly the same way as the previous speaker. Now we sample all this the electrolyte solution from the different depths of discharge, and then each depth of the discharge, and we can measure the distribution of the polysulfide species for each one of the step. Now this one is D1. Now you only see the sulfur. Okay, this is the cathode light, and the D2, and you're going to see starting of the polysulfide, and this is in the solution. Remember, not on the surface. Then D3, and you go all the way up to the D12, which is about here. Then this is the amount of the polysulfide still remain in the electrolyte, and of course, majority of them will become solid, either Li2S2 or Li2S, which we cannot measure. In this case, this is all measured in the solution. So now what we did is we're trying to plot, all this distribution of all the polysulfide species, including S8, along the discharge, okay? Then this is the potential. Say, for example, here, the D2, and this is the potential, this is the different potential. So the potential is the one that we take the measurement, and also, so this is against the time. Say this is the stoichiometry. So for example, this is the S7, which means based on the charge we put into the system, so the S7 should be formed. So this is the stoichiometry number of the polysulfide species. Now, if we looking at the plot of the change of the concentration during the discharge. Now, first of all, we're going to see the sulfur, okay, starting from 100% and going all the way down, okay, to 0. And then you have the increase of different polysulfide species. Now, I want people to pay attention to the shape of this curve, the change of the curve. Now, if the change of the curve is in parallel, okay? Now, if the change of the concentration is parallel, which means the ratio of this concentration is constant, okay? Because, yes, they are changing. The concentration keep changing, but the ratios between this species is in parallel. Now, if you're looking at this curve, you basically have 3 regions. One is in the beginning, okay? So this is if you're looking at here to here, these polysulfide species, they almost sit on top of each other. Now, remember, this one is normalized, so they're pretty much sitting on top of each other, which means even though the concentration is changed, the ratio remain constant. Now, when the ratio of the concentration remain constant, and then we can say that those species is at chemical equilibrium, okay? Now, the other one is during the later step of the discharge, you're going to see this curve in parallel as well, which means that you're going to have this species in chemical equilibrium, but in the middle, and you do not have those. You have a mixed change of the concentration. So that curve, okay, that result actually is very consistent with the discharge curve of the 2 plateaux. And the first one, you have the chemical equilibrium for the first plateau, and you have a chemical equilibrium on the second plateau, and in the middle, you actually have the mixed, you're changing from one equilibrium to another equilibrium. So this is the mechanism, and then we proposed. So you have the first, you have this chemical equilibrium, then you have this chemical equilibrium at later stage. In the middle, you have this pretty much straight chemical reactions. Now, for the recharge process, we're going to do the same thing, okay? So remember, this is one plateau, okay? We try to charging the system at different depths of charging, and we're taking the sample out, and we measure the distribution of the polysulfide species, and we plot them in one graph. Now, what you're going to see here is very interesting that now if you're looking at the red one is S4, you don't see too much of now this one is pretty much stable during the discharge, during the recharge. And this one, I believe this is the S3, now it's keep going down. Then all these species, S5, S7, and S8, they're in parallel. Now, they are in parallel in the beginning, and they remain in parallel, even though the concentration reduced, okay? Even though the concentration reduced, they remain in chemical equilibrium because, you see this curve of parallels. And now the other one is the sulfur. Now, we pretty much, in the end of it, we recover all the sulfur and we bring all the polysulfide species into 0. I'm going to explain that. And so in that case, we're going to say that this is pretty much only have one chemical equilibrium, which is S8, S7, S6, and S5. And that represents the whole discharge curve. Now, even though they are in chemical equilibrium, but we'll keep bringing the sulfur out, and then the sulfur become the elemental sulfur in the end. Now, people can ask me a question and say, oh, by the way, now based on your result, this is a fully rechargeable system, right? Yes, it's a fully rechargeable system electrochemically, and we can, experimentally, we can recover all the sulfur, but I have to tell you that the method we're using to recover the sulfur cannot be used practically. All right, the reason for that is you pretty much play the thermodynamic with the kinetics, okay? So if we can kinetically produce the sulfur faster than the so-called shuttle reactions, and we could bring, the equilibrium toward the sulfur. So this is we kinetically made that reaction happened. And it's pretty much that most of the method that in the literature trying to make the lithium sulfur battery rechargeable is using the high surface area, the carbon material or the nanotube, and try to absorb the sulfurs in the porous structure, and that pretty much play the same game here to slow down the kinetics. They slow down the kinetics of the sulfur diffusion. That is exactly what we play to make that the recovery of the sulfurs. I think I'm running out of the time, but I do want to explain this. Is what is the first polysulfide species formed during the discharge of sulfur? And if you look at literatures, most of people think that the S8, the cyclic S8 will become linear S8. Is that really the case? Now, what we did is we find the complex agent. And these complex agents, and trust me, if you can look at cyclic photometry, I don't have enough time to explain it, but this complex agent, when they complex with polysulfide, and the polysulfide complex become inert. In that case, they cannot be electrochemically reduced or oxidized, or they cannot have a further disproportionation and reaction. So therefore, if we put this the complex reagents in the cathode light, as soon as the polysulfide species forming during the first reduction of sulfur, it will be captured. Now, if we analyze what is come out of it, now we can pretty much know what is the first polysulfide species come out of the reduction. And obviously, that species is not S8 2-, but rather, if you're looking at the comparison, the red one and is in situ with the derivatizer, and the black one is the one without the derivatizer. Now, without the complex reagent, you're going to see the S8 coming out of it, but with the complex reagent, there's no S8, okay? So which means that S8 2- is not first species, okay? And this one explains why you see the polysulfide species. I don't think I have time to explain that, but take my word that the first species during the reduction of the sulfur is not S8 2- linear. Okay, so this is pretty much explain the mechanism of it. And in conclusion, I'm not going to read this due to the time. And of course, I have to acknowledge the financial support from the U.S. Department of Energy, ERE and OVT and BEMER program, and they support our research. Again, this is my group, and every time I have to show them because they do the work, I just here to take the credit. Thank you very much.
Thank you for the insightful talk. We have time for 2 quick questions. First, a quick. Yeah.
Hi there. Thank you for a very good presentation. So, am I correct in that you're saying that if you charge fast, so that you precipitate out the solid sulfur, you then limit the shuttle because you don't have the liquid species, the polysulfide species in solution that cause the shuttle? Was that one of the conclusions you came to?
That's right.
Yeah.
Because number one, why people add in the lithium nitride, right? And that is to slow down the shuttering effect, basically slow down the reactions. But the lithium nitride I didn't present, but we published that result, is the sacrifice additive, meaning they react. Now, what are you going to do? So I'm going to say it, but you really need to find the additive which is stable and can slow down this shuttering effect. But I can give you a hint. With what we understand, with this, the 2 equilibriums and during the charge 1 equilibrium. Now, what you really have to find out, because the reason why this disproportionation reaction is so fast is because activation energy is so low. Now, if you can find a catalyst which can increase instead of decrease the activation energies, okay, then you have a solution. And this is I think pretty much the direction we're looking at. So, of course, you have to sacrifice some of the capacities because you're not going to really looking at the very last, the equilibrium to find the catalyst. But you can find any of them along those disproportionation. You found one of those. They can slow down or increase the activation energy then you could have a winner. You could have a rechargeable battery, even though the capacity will sacrificed, but there will be a product. Okay.
Okay, apologize. I'm afraid we have to bring further questions off the session. Let's thank Professor Chu again.
Thank you.
Thank you.